Welcome to the deep dive.
Yeah.
Today, we are wrestling with a term you hear everywhere in modern cloud tech, Kubernetes, or K8s as you often see written.
Yeah, that abbreviation trips people up sometimes.
It does, but look, this technology, it's designed for massive scale. It's really the engine behind some of the biggest apps out there, making sure they run smoothly, handling deployment, even fixing itself.
Self-healing, yeah, that's a huge part of it.
So our mission today is simple. Give you the shortcut. We want to cut through some of that, let's say, operational complexity. Understand not just what Kubernetes does, but why it even exists. Why did we need it?
Good way to frame it.
At its core, then, K8s is this open source system, right,
Yeah.
for automating deployment, scaling up or down, and just managing containerized applications, usually across a whole bunch of servers, a cluster.
Right. And knowing its origin really helps understand its power. It came out of Google, designed by engineers there back in, 2014. These were folks already dealing with just unbelievable scale. Now it's managed by the Cloud Native Computing Foundation, the CNCF. But its real genius, I think, is how it enforces a desired state.
Desired state. Okay, what does that mean practically?
It means you tell Kubernetes, here's how I want my application to look, say 3 web servers running this version. And Kubernetes doesn't just set it up once, it constantly watches and makes sure that that's always the reality. If a server fails, it replaces it automatically. It guarantees the system you asked for is the one that's actually running.
Ah, okay. So it's not just deploy and forget. It's continuous management, a contract, like you say.
Exactly, an ongoing contract.
But okay, before we get too deep into orchestration,
Mhm.
kind of have to back up, right? You mentioned containerized applications. We can't really get why we need orchestration like Kubernetes unless we first understand containers themselves. That whole shift they brought.
Absolutely fundamental. Yeah, you often hear containers called mini VMs when they first came out.
I've heard that.
But, that's not quite right. It kind of sells them short, technically. See, traditional virtual machines, VMs, they need a whole copy of the operating system kernel, plus this thing called a hypervisor. That makes them pretty big, resource-heavy, and kind of slow to boot up.
Right. Takes minutes sometimes.
Exactly. Containers, they solved that overhead problem.
So what was the specific gain? Like what made everyone jump on board so fast?
It's the isolation technique they use. Containers tap into features already built into the Linux kernel, things called C groups for managing resources like CPU and memory,
Okay.
and namespaces for keeping processes separate, isolated. What this means is you don't need to boot up a whole separate OS kernel every time you launch an app.
Ah,
The application just shares the kernel of the host machine it's running on, but it stays completely walled off from other apps on that same machine.
so it's like having its own little bubble, but without needing its own entire operating system inside.
Precisely. And that stripped-down approach gives you huge gains. You get the self-contained unit, works anywhere, and it's light enough to launch in like milliseconds.
Milliseconds versus minutes for VM. Wow.
Yeah. So that old way, dedicating a whole VM, which was probably mostly sitting idle just for one web server, that suddenly looked incredibly inefficient. Obsolete, really.
And it happened fast, didn't it? Docker, the most popular container tech, seemed to become the standard almost overnight.
It really did.
Our sources were saying the cost savings, the density you get putting more apps on the same hardware, it's forcing companies to, well, plan for phasing out VMs much sooner than they thought.
It's a genuine replacement in many cases, yeah, not just an alternative.
Okay, so containers give us efficiency. How does that connect to how we build big applications now?
Well, this efficiency basically enabled the whole shift towards what we call microservices architecture.
Microservices.
Right. Before containers, if you built a really big application, it was usually one giant chunk of code, a monolith.
The monolith, heard that term too.
And managing that, updating one small part, fixing a bug, you often had to redeploy the entire thing, which was slow and risky.
Okay, I see the problem.
Microservices break that huge application down into lots of small independent pieces.
Yeah.
Dozens, maybe hundreds, each running in its own container. This gives teams agility. You can update just one small microservice, say, the login part, without touching or risking the rest of the application.
Okay, that makes sense for development speed. But wait, if you break one app into, say, 50 or 100 little pieces, doesn't that create a whole new headache?
How so?
Like managing the network between all those pieces, making sure they can find each other. It feels like you're just swapping one kind of complexity, the giant code base, for
Yeah.
another kind, managing this swarm of tiny services.
That is exactly the friction point. You've hit it. That's precisely why we need orchestration. Containers give us amazing speed and isolation for the components, but by design, they're kind of dumb and disposable. They don't know about each other. We needed something to manage that network layer, the discovery, the tracking.
Gotcha. And this ties into things like Docker Hub, too, right, where people share container setups.
Yeah, absolutely. Think about Docker Hub or similar repositories. Developers can find pre-configured container images for almost anything. Complex setups that might take days to figure out yourself, like an Nginx web server, or even a full big data stack with Spark and stuff. You can just download it and run it, often instantly.
The source material actually gave a command line example. It showed downloading, installing, and running Apache Spark with Jupyter notebooks, all mapped to a specific port in literally one line of code.
Exactly. Incredible convenience.
Imagine trying to manage 500 instances of that by hand across maybe 50 different servers.
Nightmare. Impossible, really.
So the very ease of deployment that containers bring, ironically, leads directly to this operational chaos if you don't have something managing it.
Precisely. If containers launch in milliseconds and you've got hundreds scattered across a bunch of machines that might themselves come and go, manual tracking just falls apart. And if we connect this back to, the business side, especially using public clouds like AWS or Azure or Google Cloud, the operational pain really boils down to two critical areas.
Okay, what are they?
First is the financial risk, just forgetting stuff is running.
Oh, yeah. The classic left the test server running all weekend story.
Everyone has one. When you're paying for CPU time, for storage, you absolutely need to know there aren't any orphan machines or containers just sitting there burning money but doing nothing useful.
Guaranteed cleanup.
Okay.
Thanks, Sets. What's the second one?
The second one is maybe even more critical operationally, dynamic scaling and fault tolerance.
Right. Handling load spikes.
Exactly. You need a system that sees when traffic is hammering your app and automatically spins up more containers to handle it right now. And maybe even more importantly, if a machine dies or a container crashes, you need a replacement deployed instantly, without a human having to wake up at 3 a.m.
Automatic recovery. Self-healing, like you said earlier.
Yes, and this is where we circle back. This is where orchestration, specifically Kubernetes, comes in. It's built to solve exactly these problems: tracking, scaling, recovery, enforcing that desired state.
Okay, so it gets rid of the manual tracking nightmare and handles the scaling and failures. How does it actually do that? Let's get a bit more into the Kubernetes mechanics.
Sure. So the most basic, smallest thing Kubernetes deploys isn't actually a single container. It's something called a pod.
A pod.
Think of a pod as like a little group of one or more containers that are tightly linked. They always run together on the same machine. They share resources like networking and storage. Kubernetes doesn't really manage individual containers directly. It manages these pods.
Got it. Pods are the unit of deployment.
Right. But the real magic for that self-healing and scaling is the layer above the pod. It's an object called a replica set.
Replica set.
This is where you, the developer or operator, declare that desired state we talked about. You tell the replica set, hey, I want 10 copies, 10 replicas of this pod running at all times.
Okay.
The replica set's job is then to constantly watch the cluster. It counts how many pods matching its definition are actually running. If it sees only 9,
It starts another one.
instantly. If it sees 11, maybe because a machine came back online, it might terminate 1 to get back to 10. It enforces the desired number.
So that's the self-healing and the scaling baseline right there. Pods are what run. Replica sets make sure the right number are running.
Exactly. That distinction is key. It eliminates so much manual work. The platform handles it.
No wonder it's used everywhere. From small teams running, an internal company website,
Like a CMS, yeah.
all the way up to massive scale, like you said, Google scale properties or big data pipelines inside huge companies.
Fortune 100s, absolutely. It scales up and down to the need.
Okay, let's try and tie this together. Using that analogy the source material had, it was pretty memorable. The digital lunchbox.
Yes, the lunchbox analogy. I like that one.
Connect that to these technical bits, the pods and replica sets.
Okay. So if the old way, maybe a VM was like one big container where all your food got mixed together, sloppy.
Yeah, soggy sandwich.
Kubernetes is this incredibly organized, sophisticated lunchbox.
Okay, so first benefit, isolation.
Right. Complete separation. Your sandwich doesn't taste like your banana.
And technically, how does K8s do that?
That's using things like Linux namespaces, like we mentioned for containers, but also Kubernetes adds its own networking layers. It makes sure pods belonging to, say, your payment processing app can't accidentally interfere with your website front-end pods, even if they happen to run on the same physical server. Strong walls between them.
Okay, isolation. What's next in the lunchbox?
Scaling. The lunchbox can magically expand if you suddenly need to pack more food.
Just-in-time expansion. How's that done?
That's usually handled by something called the Horizontal Pod Autoscaler, or HPA. It watches metrics, typically CPU usage or memory usage of your pods.
Right.
You set a rule, like if CPU goes above 70%, scale up. The HPA then automatically tells the replica set to increase the desired number of replicas. It can go from 10 pods to 100 pods in seconds if needed.
And then scales back down when traffic drops.
Yep, scales back down to save resources and cost. Fully automatic.
Cool. Okay. Isolation, scaling. What's the third lunchbox feature?
Immutability, or maybe you better put resilience through disposability.
Okay. Unpack that one.
It means you can just throw out one item from the lunchbox, say a bruised apple, a failed pod, and it has absolutely no effect on anything else in there. The sandwich is still fine.
Right. And the replica set just replaces the bruised apple automatically.
Exactly. That's the self-healing provided by the replica set. The system guarantees the desired state. The rest of the application stays stable and untouched by that one failure. Remove and replace without disruption.
Isolation, scaling, immutability through replacement. Nice analogy.
So yeah, in summary, Kubernetes gives you this cluster and container management that works pretty much anywhere, your own servers, the cloud, hybrid setups. It's vendor agnostic mostly. And it delivers that automation, that fault tolerance, that efficiency you absolutely need for running modern, complex, microservice-based applications at any kind of scale.
Okay, let's synthesize this then. Our deep dive takeaway. Containers came first, giving us isolation and efficiency by shrinking the OS needed for each app piece.
Right, the building blocks.
Then, microservices became the popular way to design apps, using lots of these small, independent, disposable containerized components.
The architectural pattern, yeah.
But that created chaos. How do you manage hundreds of thousands of these things? That's where Kubernetes comes in. It provides the automation, the management layer, the smarts to handle all that complexity.
The orchestration layer.
It eliminates the manual tracking, guarantees that desired state, handles failures, scales automatically. It tames the chaos.
Well put. It brings order to the container swarm.
So here's our final thought for you, the listener, to chew on.
Okay.
If Kubernetes provides this complete automated lunchbox for basically any application managing its whole life cycle, scaling, networking, isolation, what's actually left for developers or operations teams to worry about at the deep infrastructure level? Besides maybe, patching the underlying host operating systems once in a while.
That's a great question. As these orchestration tools get smarter and absorb more of the complexity, where does the application end and the infrastructure begin? That line seems to be getting blurrier all the time.
Something to think about for your next project, maybe.
Yeah.
Where does your responsibility stop and the platforms begin? Thanks for joining us for the deep dive.